Hey everybody, welcome back to physics. Today we're going to be discussing electrical circuits some more, and we're going to talk about some new equations that we're going to be using to analyze the power dissipated by our components in the circuit and how much energy they're using in certain amounts of time. So with this discussion, we want to think back to what is our goal for building an electrical circuit. Well, we want to convert the electrical energy in the circuit to some kind of energy to make our things work. Maybe we want light energy for our lamps, or we want mechanical energy to make like an electrical motor work. So if our goal is to convert energy, we want to quantify how much energy we're actually transferring in a certain amount of time. Now, if we're having, let's say we built a simple circuit with a light bulb lit up, we don't want that light bulb to just be like a flash for a second, right? Well, maybe sometimes we do, but we generally want those light bulbs to be on for a certain amount of time, right? So sometimes we want how much energy that light bulb uses, but other times we want how much power is being dissipated by that light bulb. And if you recall, power is equal to the amount of work or energy being used for a certain amount of time. So let's say we have that light bulb going and we have like a 60 watt light bulb, like something that you would normally find in your house. That means that that light bulb is always using 60 watts of power whenever it's on. And if that light bulb's on for, let's say, 3 minutes, 5 minutes, an hour, 2 hours, we could use that amount of time to figure out exactly how much energy the light bulb is using for a specified amount of time. Okay, so recalling our definition of power from when we did energy, capital P is work or energy over time. Remember, we use the word work and energy interchangeably, right? Because work is a transfer of energy. And since energy is being transferred from electrical to light or whatever we're using in our circuits, we could use work or energy in this case. In the reference table, that generally shows up as work. And work is a better term to use here because we are transferring energy from the electrical to whatever type of energy we want. Okay, how do we calculate the electrical power from our circuits? Let's say we know specifications such as voltage and amperage because we have meters to measure those kind of things, right? So is there a way to figure out the electrical power dissipated by any one of our components if we know information about the voltage, the current, or even the resistance of any particular circuit component? Well, let's recall what some of the definitions that we stated are for things like voltage, potential difference, and current. If you recall, potential difference across a circuit component, or the voltage of that component, is equal to work per unit charge, right? Voltage is in the realm of energy. If we have certain amounts of charge, let's say we have 1 coulomb of charge, how much work can that 1 coulomb of charge do? So we could see that voltage has some of the components that we want for power, right? And current is quite literally charge per unit time. How much charge is flowing past a certain point in a specified amount of time, right? So these charges are what's doing the work, what's transferring the energy to our circuit components to light things up or make things work the way we want them to. But notice what we have here. Our definition of power is work over time, and that's measured in joules per second. How many joules are being transferred every second, right? And if we have voltage being work over charge and current being charge per unit time, what if I took these two things and multiplied them together? Voltage multiplied by current is equal to, well, voltage is work per unit charge. Here we're deriving a way to calculate electrical power in a circuit. So we're using the definitions we know for voltage and current, the definition we know for power, putting all those things together to arrive at an equation that we're going to be using in some future problems. Voltage is work per charge. Current is charge over time, right? And if we multiply these two things together, we end up with work over time. That's what our power is. So we arrived at our very first equation for calculating the electrical power of any one of our circuit components. We can calculate the electrical power by just taking the potential difference across that component and multiplying it by the current flowing through that component. So if we have a light bulb and we know the voltage across the light bulb and the current flowing through that light bulb, we just take those two quantities, multiply them together, and we know the power dissipated by that circuit element. When it comes to lights, that actual transfer of energy, that power, manifests itself as light energy. For older incandescent bulbs, like the older bulbs before LEDs, before compact fluorescents, the ones with the little coil inside, like some of it's light energy and other amount is heat energy. But by knowing the power, we can now start calculate how much power and how much energy is being transferred in a certain amount of time. Okay, so we arrived at our first equation for electrical power. The power for any circuit element is the voltage across that element multiplied by the current flowing through that element. This is nice because we can calculate, we can measure the voltage, we can measure the current, we can easily figure out the electrical power without having to refer back to our original definition of power. Okay, so that's great. But what if we don't know the current flowing through the element? Or what if we don't know the voltage across the element? What if we only know something about the resistance of that circuit component? Is there another way to calculate the electrical power of these devices? Turns out there is. So I'm going to erase this. And we're going to start with this definition of power and see if there's other ways to calculate the electrical power of these devices inside of our circuit. Okay. So we know power is equal to voltage multiplied by the current. Okay. Now, like I said, what if we don't know voltage, we don't know current, but we know something about the resistance? Could we build another equation for electrical power? Well, recall Ohm's law from the last video. Ohm's law states that resistance is equal to voltage over current. So here's another equation that links up voltage, current, and now resistance of that circuit element. This is useful because sometimes those elements in the circuit, like a resistor, we know the resistance of the resistor, but if we don't have a voltmeter on hand or an ammeter on hand, we can still use it to calculate the electrical power. By the way, resistors, their goal is to resist the flow of current. Their goal isn't to light anything up or make anything move, but resistors still dissipate electrical power. If you actually set up a circuit with a resistor and a battery and you touch that resistor, sometimes that resistor starts getting hot. So the way that it resists the flow of current, it starts taking energy out of the circuit in the form of heat energy. Okay, so let's rearrange this for a second. Let's say I know the current flowing through the component and I know the resistance of the component. Can I use those two quantities to figure out the electrical power? Well, if we rearrange Ohm's law, we get V equals I times R. Here's how it shows up in your reference table, but we could always mathematically rearrange things. So I know the voltage across an element is equal to the current multiplied by the resistance. What if I just take this and dump it right into my power equation here? So power is equal to voltage times current, but we know that voltage is also equal to the current times the resistance. So we could say that where I see the V, I can plug in I times R. That I still stays there. Because now I had an expression for voltage, I could just plug it in. So now we arrived at another way to calculate the electrical power of any circuit element. I I times I is I squared multiplied by R. There's another way to calculate electrical power, another equation. This is useful if we know the current, we know the resistance, but we don't know the voltage. We can use that equation. Okay, last question for you. What if I know the voltage across the element, I know the resistance, I don't know the current, can we still figure out the electrical power? Well, let's see, let's play around with the equations that we have. I'm going to do that over here. Again, we know Ohm's law is equal to V over I. And rearranging this, I could get an expression for current. Right? If we don't know the current, then we want some way to substitute it out. So if I know the current of the element is voltage divided by resistance, I did that by just rearranging it algebraically. Let's now look at our power expression here. Electrical power is voltage times current. Let's say I don't know the current, I could plug in this expression here, V over R, wherever I see the I. V is equal to V over R. Power is equal to V times V over R. V times V is V squared, so we could simplify and say the electrical power could also be found by finding V squared over R. Okay. Again, all of these expressions are useful to us because depending on what we know electrically about these components, we can always find some way to find the power dissipated by that element and in turn figure out how much energy is being used by that element. So if you look in your reference table, page 4 is where you find the electrical equations. You will see a long string of equal signs that look like this. P is equal to V times I, which is also equal to I squared times R, which is also equal to V squared over R. All right, so if a question asks you, what's the power dissipated by an element, or how much power is being used by an element, you can use any one of these depending on what information you know. Don't get confused by this long string of equal signs. It's just saying that you could use any one of these expressions. You can use P is V times I, P is I squared times R, P is V squared over R. This is just a way to put it all in one place. Okay, that's how we determine the electrical power used by any circuit element. But what if we're interested in how much energy is being used, right? Power is work over time or energy over time. So let's say I know that my circuit was on for 20 minutes or it was on for an hour. Maybe can we use that amount of time to figure out how much energy was actually used over that period of time? Okay, take a second, write this down. This is the most important thing. We're going to be using these expressions to answer some problems about circuits. All right, I'm going to erase. I miss you guys. I'd much rather be doing this in class than in my basement. I hope everyone is doing well and staying safe. Okay. So, to figure out how much energy is being used by any circuit component, we want to go back to our definition of power. Power is equal to work over time. How much energy is being transferred, the rate of energy transfer, right? The time rate of change of energy transfer. So how much energy is being used in a certain period of time? Well, let's rearrange this. Multiply both sides by T. We can say work is the amount of energy that that circuit component is using, whether we're looking at a lamp, a motor, it doesn't matter. This is the amount of energy that component's using. It's equal to the power of that element multiplied by time. We did this when we were doing energy, mechanical energy, back a few months ago. So we have an expression for power. Not only that, we have a bunch of expressions for power, right? P is VI, P P is equal to I squared R, and P is equal to V squared over R. So if I take any one of these expressions and multiply it by how much time that circuit element was on, we can figure out the energy used by that element. So underneath this line in your reference table, you will also see this. Work, the energy used by any circuit element, is equal to power times time. You knew that already from when we were doing mechanics. But now we have all these electrical expressions for power, so we can plug them right in. VI multiplied by T. Or I squared R multiplied by T. Or, get a little sloppy here, V squared T over R. By taking any one of those expressions and multiplying it by how much time that circuit element was on, we know the amount of energy that that circuit element used. Okay. So like I said before, these are the two most important string of equations that we want for this particular lesson. Here's how you can find the power from any circuit element, and here's how you can find the energy used by any circuit element. All right, let's use these and work out some problems. Make sure you write this down. I'm going to erase. Whoa. There we go. Boom. All right. Let's try a problem. Let's say we have a light bulb. And that light bulb is connected to a 3-volt power source. Light bulb is connected to a 3 power source. It draws half an amp of current. We want to find what is the power dissipated by the light bulb. That terminology, the power dissipated, it's just saying that the energy is leaving the circuit in the form of light, in the form of heat. So that's why it's power dissipated by the bulb. And we also want to know how much energy is used in 3 minutes. How much energy is used by the bulb in 3 minutes. Okay. I'm going to do part A on this side, part B on this side. So, what's the power dissipated by the bulb? You want to think to yourself, power dissipated. We look at our reference table and we see all those different expressions that we could use to find the electrical power of that bulb. And we saw that the very first one we discussed was potential difference, voltage, multiplied by current gets us power. So we could use that first equation. So for part A, we can say that the power dissipated is equal to voltage times current. Well, we know that it's a 3-volt power source and it's drawing half an amp of current. So the power dissipated is equal to 3 times a half is equal to 1.5. And think back, what was our unit for power? Just because it's electrical power is not anything different from the power we discussed before. The unit is watts. Shh, I'm filming.
Sorry.
All right, so the power is watts, 1.5 watts. So using what we found, we can figure out how much power is being dissipated. And again, think back to what voltage and current means. Voltage is work per unit charge, and the current tells us how much charge is flowing in a certain period of time. By multiplying those together, we get the power of that circuit element. All right, then it says the circuit is on for 3 minutes. How much energy is being used in those 3 minutes? Well, we know the power is 1.5 joules per second. For every second that the circuit is on, it's using 1.5 joules of energy. So if it's on for 3 minutes, how much is being used? How much energy is being used? Here, we could go back to the definition of power by multiplying both sides by T. We know the work or the energy used by that component, the energy transferred, is the power multiplied by the time. Okay, we know the power is 1.5 watts. Remember, watts is joules per second. So can I plug in minutes for the time? We can't. You have to make sure you keep everything in SI units so we don't get mixed up. Oh, excuse me. I messed up here. We want the energy. We know the power is 1.5 watts, right? And the time is 3 minutes. So 3 times 60 is 180 seconds. 1.5 joules per second multiplied by 180 seconds. This circuit component uses 270 joules of energy in that time. Okay. So, using our equations, we could find what is required for the problem. And think about how useful this is. The fact that we understand the power dissipated by the component and how much energy is being used. Not only that, but some circuit components have specifications of the maximum amount of power that can be delivered to it without it failing. Like if you deliver too much power to a resistor, believe it or not, it could quite literally burst into flames. So we want to make sure that we are delivering the correct amount of power. And by understanding how this stuff works, we can make sure that we don't fry any of our circuit components. Okay, I'm going to erase. We're going to try another problem. Okay. Let's say, for our next problem, we have this simple circuit here. We have this is, let's say, was just given to you. Okay, this is labeled as 120 volts, and this is labeled as 480 ohms. Now, a few videos ago, if I just gave you this, you wouldn't understand what is being given here. But now we have enough information to analyze and understand what this circuit schematic is telling us. We have a 120 volt power source, and it's being delivered to this resistor. And that resistor has a resistance of 480 ohms. There's an ammeter hooked up in the circuit, but the reading on the ammeter is not given. What we want to know here is A, find the power dissipated by the resistor in the form of heat. By the resistor. And we want to determine the reading in the ammeter. So we have a new tool to analyze electrical circuits, right? Now that we know how to calculate electrical power and energy, we can use that to figure out things like the reading of the ammeter. But first, we want to find the power dissipated by the resistor. Energy needs to be transferred out of the circuit if we're going to resist the flow of electricity, and that happens in the form of heat. Okay. So let's see, we want electrical power, so I'm going to start with, here's part A, by the way, power. Well, we have a few different options of how to calculate electrical power, right? We could do voltage times current, but I don't know the current yet. We could do I squared R, but again, I don't know the current yet. But we see that the last expression that we found was that we could find the electrical power by taking the voltage across the resistor squared and dividing it by R. That is a valid expression, and we can use what's given to find the power. Now you might be asking yourself, well, I don't know the voltage across the resistor, but I do know the voltage of the source here. What we're going to be talking about in future videos is that this 120 volt source creates a potential difference between this point and this point. And then that potential difference actually is still 120 volts from this point to this point. If that confuses you, don't worry about it too much now. We're going to talk about it in a future video. But by knowing the voltage source and only having one component in the circuit, ignoring our ammeter for now, we know the voltage across this component is 120 volts. Okay. P equals V squared over R, that's 120 volts, squared divided by 480 ohms. So we get the electrical power. Again, pause the video, work it out yourself, but that electrical power, when you work it out, should be 30 watts. There we go. So we know the power dissipated by the resistor is 30 watts. Okay. And again, so if we let this circuit run, that means 30 joules is being dissipated every second that the circuit is on. That's what that power means, 30 watts. Okay, next what we want to do is determine the reading of the ammeter. So for that, the reading of the ammeter, if you recall from previous videos, ammeters measures current. It's literally counting how much charge is passing this point every second. So how do we determine the reading of the ammeter? We need to solve for I somehow. There's actually two ways to work this out. First, let's look at it from a power perspective, because that's what this video is all about. But you can also use Ohm's law to figure this out as well. Either way is 100% valid to work out this problem, and whatever you're more comfortable with, feel free to use. Okay, from a power perspective, part B, we know power is equal to I squared times R. We also know, since we found it before, 30 watts of power is being used by that resistor. We want I, and we know the resistance of the resistor is 480 ohms. We could work that out to figure out that I is equal to, work it out, 30 divided by 480, take the square root, is equal to 0.25 amps. A quarter of an amp. There we go. Let me move all this stuff here. Okay. So I said we could do this in two ways. We could use the power, or we could use Ohm's law. If we use Ohm's law, it looks something like this. R is equal to V over I. We know the resistance and we know the voltage. So the resistance is 480 ohms. The voltage is 120. If you solve for the current, you'll get the answer of 1/4 amp. So we predicted the reading on the ammeter just by knowing these specifications before we even looked at the ammeter. All right, and that is it for this video. As always, if you have any questions at all, feel free to reach out. I'm here for you. In future videos, what we're going to do is we're going to dive in and figure out how do components actually resist the flow of electricity? What kind of physical qualities go into making these resistors? But we'll save that for next time. Hope everyone's doing well, and I'll see you soon.